Earlier in this course, we found that matter comes in atoms and that currents come in electrons. Now what about light? Are there light particles? Well, I'm going to show you an experiment which proves that there are. Now you remember that we didn't see the effect of electrons till we had very weak currents, nor did we see the effect of atoms until we had small amounts of matter. And we're going to have to use very weak light in order to see the effect of the light particles. Now how do we study light? We can use a photoelectric cell. Here is one. It consists of a metal plate in an evacuated envelope. And when light strikes this plate here, electrons are emitted, and they're collected by this little electrode in here. And the amount of current is proportional to the amount of light striking the tube. And if you have very dim light, you don't get much current, so you need an amplifier. Now, we can use a photomultiplier, which is a photoelectric cell with an amplifier built into the same bulb. Now, you can't see how it works here, but I can show you on the blackboard. It consists of a number of plates, something like this, and the light comes in and strikes the first one, and some electrons are emitted. Here's one, for instance. It's attracted to this plate by a voltage of perhaps 100 volts applied to it, and when it strikes the plate, it knocks out 4 or 5 electrons, and they're attracted to the next plate, something like this. And each of the electrons that strike this plate, in turn, knock out 4 or 5 electrons, and they are attracted to the next plate, and so on. And eventually you get a pretty heavy current, and you can collect it after you've had enough multiplication. And with a tube such as we have here, with 9 stages, the multiplication is about 1 million. To check that, we can use our sensitive ammeter first to measure the current going into the first stage, and then to measure the full output at the collector here. That current should be 1 million times greater than this one. Let's do it. I have here a sensitive ammeter, which I can use to measure the current going into the first stage of the multiplier. Let me put the tube out where it gets some light. And you see I have a reading. And when I keep the light from going into the tube with my hand, the reading goes away. Now that's much too much light to use with a sensitive device like a photomultiplier. So let me turn off some lights. Now let's see what our reading is. It's 5 times 10 to the minus 11th amperes going into the first stage of the multiplier. Now we will read the full output of the multiplier. So let me connect it up. And with the same amount of light, I find that I have to go down 1, 2, 3, 4, 5, 6 powers of 10 to get about the same reading. So we conclude that the amplification is about 1 million, as we said. Now let's put the output of the photomultiplier on the cathode ray oscilloscope. And now I'll cover it with my hand, and then take my hand off suddenly, letting the light in. There, it responds. I'll do it again. Now I'd like to use weaker light, and I guess I'd better connect in this little amplifier. And you see there are pulses. Now we have weak light and we see pulses. Does this mean that light comes in particles? Well, not necessarily, because remember how this works. Light comes in and it makes electrons come out of the first plate, and they're amplified in here. And then you see it on the scope. And so naturally you see pulses. We know that electrons are particles. We have to do some other kind of experiment to prove our point. Now, there's another effect of photomultipliers that I want to show you, and that is that even when I exclude all the light by covering it with a black cloth, you still see some pulses, not as many. And this background is an effect that is common to every kind of physics experiment. Fortunately, we can get rid of most of it by cooling the photomultiplier. And I'm going to do this with dry ice and alcohol. Let me put the tube in this box. Put in some dry ice and some alcohol, and that will cool it nicely. Now I've described to you our apparatus. What sort of experiment are we going to do? Well, let me explain it to you with an illustration. I'm going to assume that you're very fond of milk, and that you have to have a quart of milk once a minute. And I'm going to supply it to you in a rather strange way. Behind this wall is a vast amount of milk, capable of flowing at the rate of 1 quart every 10 seconds. And once a minute, this gate opens for 10 seconds. So the milk starts flowing out, and at the end of 10 seconds, you have your quart. In this case, the milk is packaged in quart cartons, distributed along this conveyor belt in an arbitrary way, such that 1 quart goes by any point, on the average, every 10 seconds. This gate opens once a minute for 10 seconds, just as this one did. Now, is there any way that you can tell whether the milk is in bulk or packaged just by what happens down here? Not by looking through the gate or by looking for cartons or anything like that. Certainly. All we have to do is watch. When the gate opens, the milk starts flowing in this case, and it takes a full 10 seconds to get a full quart. But in this case, when the gate opens, a quart might come through right away, or 2 quarts, or 3 quarts, or none at all. On the average, of course, you'd get a quart every time the gate is opened. Now, you don't know either when the quart will come through during the 10-second open time. It might come through right at the start or at the end. Here there is no consistent delay in the arrival of your milk. But here you must always wait for 10 seconds after the gate is open before you have your full quart. This is the idea that we are going to use to find out whether light is packaged or in bulk. Here's our light source. And here is a shutter which plays the same part in our experiment as the gate did in our illustration. It consists of a disc with a hole in it. And every time the disc goes around, this hole lines up with a hole in this plate and lets light through. The disc is driven by an electric motor that you see here. Here's a drawing of the apparatus. Here's the light source, the shutter, and the photomultiplier. Light will reach the photomultiplier only when the holes in the shutter line up. This will happen for a brief instant during each revolution of the disc. What we are going to do is look for a delay in the emission of photoelectrons after the light strikes the photomultiplier. Now let me line up the whole apparatus, and I will use our ammeter to tell me when light gets through. I'm turning the motor shaft so that the holes line up, and light gets through. Now the meter reading is maximum. I'll shut the light off with my hand. Now that's a pretty strong light, and I want to reduce the intensity so that first let me put on this shield which will keep stray light out. And now I'm going to use these filters which reduce the light intensity by a factor of 100. Let me put one in. The reading now is 3 times 10 to the minus 4th amps. I'll put it in. And now I get 4 times 10 to the minus 6th amps, a factor of 100. Let me put in another. That's about 5 times 10 to the minus 8th amps. Again, a factor of 100. And I'll put in a third. Well, now I have to use so much sensitivity that the meter reading isn't very steady, but it's about 3 times 10 to the minus 10th amperes. Now that's the current coming out of the photomultiplier when there are 3 filters between it and the light. But look, this is the output of the photomultiplier. 3 times 10 to the minus 10th amperes. What is the input? That's this current produced by the light. And we figured out that this device had an amplification of 1,000,000, so that that current must be 1,000,000 times smaller, or 3 times 10 to the minus 16 amps. Now we can express that current in terms of the number of electrons per second. It's about 2,000 electrons per second. Which means, on the average, 1 electron every 2,000th of a second. 1 electron per 2,000th of a second. Now this is just the same sort of statement as 1 quart of milk every 10 seconds. Now when the milk came in bulk, we always had to wait a full 10 seconds after the gate opened before we had our quart. And if light comes in bulk, we'll have to wait a 2,000th of a second at this intensity before we get an electron. Now, if the milk was in packages, we would sometimes get a quart right away when the gate opened. And if the light is in packages, we may sometimes get an electron the instant the shutter opens. Now let's do our experiment. I'll turn on this motor, which spins the shutter at 60 revolutions a second and lets the light through for a brief instant 60 times a second. Now I'll connect the photomultiplier to the cathode ray oscilloscope. And so we can see what we're doing, I'll take out these 3 filters. Here's where the shutter is open. Now, you notice that I've synchronized the sweep of the cathode ray oscilloscope with the rotation of the disk, so that the on period always takes place at the same point. How long is that on period? Well, I can measure it with the cathode ray oscilloscope, or I can figure it out from the geometry of the disk. It's about a 5,000th of a second. Now let's expand the sweep. And now you see the pulse more clearly. Let me mark the start and finish of it. From here to here is a 5,000th of a second. Now I'm going to put in a filter that reduces the light intensity by a factor of 100. I'll need more amplification. And you can begin to see the effect of the electrons. Let me put in the second filter. More amplification. And now you can distinguish individual pulses. Notice also that there are some pulses outside the on period. This is the background. It has been greatly reduced by the cooling of the photomultiplier. Now I'll put in our third filter. The light intensity will then be so low that we'll only get 1 electron every 2,000th of a second on the average. But look, this is a 5,000th of a second from here to here. A 2,000th of a second from the time the shutter opens is out here, well after the shutter is closed again. If we had to wait a 2,000th of a second before getting any electrons, that is, if light comes in bulk, then we couldn't get any electrons at all because the shutter is no longer open. But we do get them. We not only get them in less than a 5,000th of a second, but in fact almost when the shutter opens. Let's stop the film and look at a pulse that occurred right after the shutter opened. I measured this one and found that it occurred 6 microseconds after the shutter began to open. Here's another with a delay of roughly 6 microseconds. We see pulses within times that are small compared to a 2,000th of a second. Now what does this mean? It means that light does not deliver its energy in a continuous stream, but in particles. Remember our illustration. When the milk was in bulk, it always took 10 seconds after the gate opened before you got your quart of milk. If light is in bulk, we would expect 1/2000th of a second delay between the opening of the shutter and getting any electrons. Experiments like this and many others have convinced us that this is the right interpretation. But these particles, called photons, are not the same kind of particle that Newton talked about. For one thing, they are intimately connected with waves. We're going to show you experiments in which you will recognize the photon, and at the same time, you will see wave phenomena. Waves and particles, we need both concepts to describe the behavior of light.